In the last video, I talked way too much about what is a Riemann sum and what does it mean. Let's actually do some math. Let's try an example. So this one says use Riemann summation to approximate the area underneath the curve f of x is equal to 10x minus 2x squared on the interval 0 to 5 using the following number of subintervals. So here I've graphed the function. I did not label it, but basically this is starting at 0, 1, and 2, and so forth. And this would be x, and then this would be f of x. And our function, let's just write it down here again, just for the record, is 10x minus x, or 2x squared. And let's say we wanted to know how much area is under the curve. And again, we could use a Riemann sum, which is just basically breaking it into rectangles to approximate it. And it says to draw the subintervals in the graph, and it says let's do this twice using two subintervals. N is equal to 5 and n is equal to 10. Notice it does not tell us should we use a left sum or a right sum. Your homework should tell you, and let's just go ahead and practice using a right sum, not for any particular reason, but let's use the right sum instead of a left sum, because the book talks a lot about left sums and it's shown in this particular example. But all that means is, okay, I'm trying to break this into 5 subintervals. And also, if we're talking about a specific interval, we often call this between A and B. And if you remember on the last slide, there was a formula. If you're wondering, well, what is delta x going to be? Delta x is always equal to A, or B minus A. Let's just revisit where that formula is. B minus A divided by n. So let me write this, B minus A divided by n. This is the generic formula for how to find delta x whenever you're trying to do a Riemann sum. But here, basically it's like the width of our interval is 5 minus 0, and we're trying to separate it into 5 subintervals, n is equal to 5. Or basically our delta x is going to be 1 here. And like here, I tried to make it very, very obvious and easy, because if I'm trying to break this graph into 5 subintervals, I just have 5, I go from 0 to 1, 1 to 2, 1 to 3. And essentially, I'm just going to break it down like this, and this, and this, Those are going to be my columns. But you could do it in any number of n. It's helpful to make it divisible by your width of your interval. And remember, width of the interval is just, 5 minus 0 is 5. This is the width here, divided by something divisible so that it's easier to divvy it up. But basically, if I'm going to use a right endpoint, it's like here's going to be my column. And the question is, well, where does it connect? But remember, you're connecting it to your function. You could connect it on the left-hand side, on the right-hand side, or even on the midpoint. Any method is fine, but we'll just use the right-handed Riemann sum. It does not specify, but basically, again, I'm going to use this segment of area right here for my first interval. Because again, it's connected to the curve on the right point. And again, for every other point, basically I just want to take the right-hand side of the interval, connect it to my curve, and build a rectangle there. So this would be my second segment of area. My third one would connect to right there. My fourth one would connect to right here. And then the fifth one would actually connect at the very bottom. And remember, sometimes it might be a little bit hard to visualize where those bar graphs are. But essentially, sometimes it will be way above, sometimes it will be way below. It just depends on where the function connects. What you want to be careful is to, if you have, again, it's like here's my interval 1, my subinterval 2, and we use the subscript in a Riemann sum to represent each of the n groups. You want to use the right endpoint where it connects to the function on the right-hand side. So, I'm going to clearly label that with a dot here so I can see that it's consistent. That's the only thing you need to be consistent. Do it the same way every time. You can't just pick and choose where you connect it. And if it were a left one, it would look a little different. It would be here, 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 and here. But actually, due to the symmetry of this graph, it wouldn't actually make a difference. Anyways, now what? Well, again, the goal is to find the area underneath the curve. And looking at this graph, since it actually has been labeled using 1, 2, 3, 4, 5, 6, and 7, you could just sort of say, okay, this area is, they're all delta x is 1. So the width of them all of these rectangles is 1. Now the height is the thing that changes. Here it's height 1, 2, 3, 4, 5, 6, 7, 8. So the area of this would just be 8 times 1. This one would be, well, 12 times 1. And you can find the area just by looking at it. But let's practice using the Riemann sum math, because that is the important idea. So again, what we'd have is, well, we'd have f of x1 times delta x plus f of x2 times delta x, and so on. This is the formula for the Riemann sum on the previous page. Or again, we could write that using summation notation. Delta, the sum of all of the f of x's were from the index times delta x, because again, delta x is a common factor in all of those, and we want to add up all 5 of them as the index goes from 1 to 5. So again, this is how we compactly write that. So like again, imagine you had 20 subintervals. You'd have to write this out 20 times. It'd be very, very tedious. But it's just a little bit more simple to write it in a compact form. But at the end of the day, that's what we need to do, is we need to multiply length times width plus length times width times length times width, and so forth. So if we were to do this, well, what I need to know is, well, what is f of x1? So, starting with this one, this one right here would be the location, what we call f of x1, because that's the height of the first bar. And then, so if I was to go ahead and solve that, that would be this, and I would need to multiply that times delta x. And, I could just use the formula. So if you're paying attention, to the x-axis, this was 0, and again, notice how I've labeled this as starting to get a little bit confusing, but let me go back to the normal x-axis. Well, on the x-axis, this was the origin. So this was x equals 0, x equal 1, x equal 2. Again, this is different than delta x, because delta x is always just 1 across the board. And notice that it doesn't necessarily match up with the labeling of the subintervals. But basically, f of x1 occurs at exactly x equal 1. So f of x1, basically, this is x1. It's equal to x of 1. And again, usually this is not going to happen coincidentally, but essentially you need to figure out what is f of 1 and multiply that by delta x. And then for the second height value, the value of the second rectangle there, it would be right here that determines this. Again, notice that occurs specifically at 2. So this would be f of 2 to get that. But essentially, you could just look at the graph to visualize the area, but the point is you can use the function instead. That's the more mathematical way of doing it. Plus f of 2 times delta x, plus f of 3 times delta x, and so forth. F of 4 all the way up till f of 5. And also, we could just factor out delta x from all of that, obviously, which is kind of what this is saying. Because delta x is treated as the same across the board, it could be factored out. So essentially what I'm going to have is f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 times delta x. And this would give me the sum of the exact same thing here. And, again, f of 1 we determined to be 8. We determined to be 8 from the graph. Sorry, I'm trying to get my pen working right. But also you can use the function. This is the whole point that I'm trying to get across here, is in order to evaluate the area, you don't even need a graph. You don't need the area. You can actually just do this math upon the mathematical function. Because f of 1, well, if I just plug in 1, I can clearly see that's 10 minus 2. That gives me 8. Again, it's consistent with the graph, and this helps us imagine what we're doing. We're finding the area under the first little rectangle. The second rectangle is determined by f of 2. Now, if I plug in 2, I would have 20 minus 8. That's 12. Again, that's consistent with the graph, the height value over there. And now if I want to know f of 3, I plug it in here. So this gives us an idea of how do we find the area under curve. Well, you plug it into the function in a lot of different places, add them all up to properly get the area under the curve. And as long as you're divvying it up using delta x and finding x1, x2, x3 correctly, it should work out just fine and sensibly. And this is kind of the most straightforward way to approach this. Now, f of 3 would be 30 minus 2 times 9 is 18. 30 minus 18 is also 12. Again, notice it happens to have the same height in both of those two coincidentally, but there we go. Now looking at the next one, I would expect this one to be 8 because it looks to be level with the one over there. But let's, again, just do the math. F of 4 would be 40 minus 2 times 16 is 32. 40 minus 32 is 8. Yes. And then when I look at f of 5, I'd expect that to be 0 because that's where x equals 5 ended up. And this would be 50 minus 2 times 25. Yeah, 50 minus 50 is 0. And again, delta x was just 1. So what I end up getting is, well, 20, 40 times 1. 40 times 1 is 40. And that gives me the area underneath the curve. Or again, it's an approximation to the area of the curve, but we would refer to this as the Riemann sum of this curve for these particular values. And your homework will give you a couple problems. I try to not give you too many because these take quite a while to figure out. There's a lot of mathematical calculation in a Riemann sum. And again, this gets way easier once we learn how this translates to calculus. But the whole point is understanding what a Riemann sum is, the connection and the fundamental theorem, stuff we're going to work on Monday in class. And in the next video, we'll talk about doing it with 10 subintervals instead of 5.